Okay, so today we want to do a little bit of review for our second exam, which is coming up either Wednesday or Friday, depending on who you are. I think we're going to do it exactly the same as we did last time, where the A and C groups are going to have their exam on Wednesday, and then the B group will have their exam on Friday. So let me write that down. So group A, C on Wednesday. And then group B on Friday. Okay, so let's talk a little bit about what to expect on the exam. I think it's pretty straightforward on this chapter just because it's just been a bunch of integration techniques, right? So we're just learning all these different ways to compute the integral. And now when you look at them all, there's quite a few. We've talked about using polynomial division. These first three were kind of in that very first section on basic integration techniques. But wait a second. Yeah, it's here. Okay. We have polynomial division, completing the square, using some sort of a trig identity to help you. And then we got into the more advanced techniques like integration by parts, trig integrals, trigonometric substitutions. Then we did partial fractions, and then we left off with improper integrals. So how will the exam look? I don't think that you'll have time to do like 10 of these problems. So it probably will be somewhere between 6 and 8 problems, depending on the problem that will be on the exam. And you can expect to have about one of each. Let's see, how many total do I have here? 3, 4, 5, 6. I have 8. Whoa. Interesting. So you could kind of expect that you would have maybe about one of each of these things. And again, the hard part of this exam isn't per se doing each of the techniques. The tricky part is diagnosing which technique to use when. And the only way to really get good at that is doing it. So the way to study for this exam is do a bunch of problems. And it's much better to not know where the problem's coming from when you start it. So what I would do if I were you is find a friend in the class and get together, pull out your book. One of you have the book, the other one doesn't see it. You give them a problem, and then you just say, what's the technique? Now, working the problem would be good too. That's good practice too. But if you want to just start with like, okay, here's a problem. What should we do? Like, let's say that the problem is integral of x squared cosine x dx. And really all you want to know to start out is like, what should we do? And what's the answer?
Integration by parts.
Yeah, integration by parts, right? This is an integration by parts problem. And if you see that, it's really not too bad. If you don't see that, maybe it's impossible. Okay, so the first thing you need to get good at is just diagnose the different situations that could come up. Once you are good at that, it's not that bad. Like, I think you've done all these things, so you know how to do them. But sometimes saying, oh, which one is it, is the hardest part of the problem in some sense. So any questions about the exam or what could be on it, what won't be on it, anything you need to know?
What won't be on it?
What won't be on it? No history.
Okay.
I don't know. I guess there will be a lot of things that are not on it. But is there any, what I mean by that is anything specifically that you're kind of like, this was kind of a weird thing that showed up in a section. Would you ever put that on? Yeah.
Like revolution.
Right. You mean like, would I ever ask you to compute the volume of something that's spun? On this exam, no, I won't. On the final, I would, but no, not on this one. Other questions? Yes, sir.
We won't need like the reduction formula stuff.
Yeah, I won't expect you to use any reduction formula. So a good question though is like, what do I expect you to know? Right? Like just off the top of your head. Obviously how to do all these things, but especially people are kind of wondering, well, what about like trig stuff? Do you expect me to know any trig stuff? And it's like, yeah, actually I do. I would say, the obvious thing is just that sine squared x plus cosine squared x equals 1. That one's pretty straightforward, but I do expect you to know it. The other one is that 1 plus tan squared of x is equal to secant squared of x. That one comes up a lot, right, when we're doing trig substitutions. So I would expect that you know that. Also, half angle identities come up a lot in these problems, and I would expect that you know the half angle identities. So what's that? Sine squared of x is equal to 1 minus cosine 2x over 2, correct? And then cosine squared of x is equal to 1 plus cosine 2x over 2. And anything else? These are the big ones, especially the half angle identities, because you definitely need to know half angle identities for some of the trig integrals. Okay, especially if you have like an even power of both sine and cosine involved, you have to use half angle identities to get the job done. Other than that, yeah.
Do you have to know like the sine inverse ones? Like the
Yeah, so any derivative that's like a cow1 derivative, I would expect you know. So I'd expect you to know all the derivatives of the trig functions, all the derivatives of the inverse trig functions, all of the antiderivatives of all those things. Same with like exponential functions, logarithmic functions. So all of kind of your basic calculus functions, I would expect you to be able to take the derivative and the antiderivative. Yeah. Anything else? All right, then just as a reminder, we still do have Math Lab open and Lemons 15. And that's not a bad place to go if you're needing a little bit of extra help in the next couple nights. There's lots of whiteboard space in there. You could just go in, find a friend, just do some practice problems. And if you get stuck, there's somebody there to kind of bounce ideas off of. That's a good way to go. In terms of myself being available for some time, I will be around tomorrow. But I don't have an official office hour tomorrow. So if you want to get together and ask me a question, email me, and that would be the best for tomorrow. So, okay. Any questions that I can just answer? Any example problem you'd like me to work on for you? What can I do for you in the time we have left? Yeah.
Is it possible to like do one of each problem?
I certainly could. So what would you like to start with?
We could start with polynomial.
Okay, I'll have to find one. All right. Oh, there's one. Let's see. So we have the integral from 2 to 4 of x squared plus 2 divided by x minus 1 dx. Okay, so this is a polynomial division problem, and the way that you know that maybe polynomial division would be the right way to go is you need to look at the power of x on the bottom and the top. And typically you have a polynomial over a polynomial, and the power of the thing on the bottom is less than or equal to the degree on the top. So the degree on the bottom here is 1, the degree on the top is 2. And if they're equal or the one on top is bigger, that means you could divide that thing in. Okay, if the one on top is smaller, then you don't do this, okay? If the power on top is smaller, typically if the power on top is smaller, you should be thinking partial fractions. It is possible that you could get into a situation where you do polynomial division, and then what's left over, you need to use partial fractions. That would be a mean problem for me to give you on an exam, but it could happen. But what I see here is the power on top is bigger than the power on the bottom, so that's a very good time to try polynomial division. So what we want to do is we want to divide x squared plus 2 by x minus 1. So we just use long division, and we say how many times does x go into x squared? Or what times x gives me x squared? And the answer is x. And then I multiply, so x times x is x squared, x times minus 1 is minus x, then I subtract, and x squared minus x squared is 0, and then I get positive x, and so, well, there's going to be a 2, but there's going to be a plus x. So I get x plus 2, it's left over. Okay, then I say how many times does x go into x? 1, so I add 1. Then 1 times x is x, 1 times minus 1 is minus 1, and I subtract. And x minus x is 0, and 2 minus minus 1 is 3. And how many times does x go into 3? It doesn't, so we're done. So the way that I would normally do this if I were just doing a long division problem is I say, okay, it went in evenly x plus 1 times, so I get x plus 1. And then there were 3 left over, and they're still divided by the denominator. So plus 3 over the denominator, which is x minus 1. So I've turned this thing into this thing. And so now I could rewrite that this is the integral from 2 to 4 of x plus 1 plus 3 over x minus 1 dx. That's much easier to deal with. I know how to take the antiderivative of everything. I'll erase this really quick. So now I could rewrite as antiderivative of x is x squared over 2. Antiderivative of 1 is x. Antiderivative of 3 over x minus 1, what's that?
3 ln.
Yeah, 3 ln absolute value x minus 1. And all of that is evaluated from 2 to 4. So now we just plug things in. Plug in 4. 4 squared is 16 divided by 2 is 8. plug in 4 plus 4. Then I get 4 minus 1 is 3, so I get 3 ln 3 plus 3 ln 3. By the way, this is also otherwise known as like ln of what?
27.
Yeah, 27, right? It's ln of 3 cubed, because you could put this up as a power of the 3 if you wanted to. It's just good to remember. Minus, now plug in 2. 2 squared is 4, divided by 2 is 2, plus 2, plus 3 ln of 1. ln of 1 is 0, so that's just 0. So minus 4. So I get 8 plus 4 is 12, minus 4 is 8, so I get 8 plus 3 ln 3. Which is fine if you put 8 plus ln of 27, also fine. Yes, sir.
37 and 8 1 is
37.
5.
Yeah, I think you're right. Okay, 37 and 8.1. Sure. Let's look at it. So this is 37 in 8.1. And it says integral d theta divided by the square root of 27 minus 6 theta minus theta squared. Okay, and like I said, this is probably a complete the square problem. And the way that I know that it's a complete the square problem is I kind of have on the bottom, it might be a square root, it might not, but it's a quadratic. Okay, and wouldn't it be wonderful, sometimes when there's a quadratic on the bottom, we want to do partial fractions, right? So how do you know? Well, the way that I would look at it is it's kind of like, well, can I factor that thing? Is there a nice thing that, let's see, we need 2 things that multiply to 27 and add to -6. But also there's a negative here. So, okay, the first thing that I might do is say, this is a mess and it has a negative on the square. That's not really that nice. So let's get that like factored out. So I might just rewrite it this way. So I have d theta on the top. On the bottom, I don't like that negative there. So let's just factor out a negative, and then I get a theta squared. This becomes a positive 6 theta plus 6 theta. And then I could say that this is a positive 27. Maybe I'll just leave it out by itself though, because what I want to do is complete the square. So we have plus 27. And now the question is, what should go right here to complete the square so I can just write this as something squared? What should go here? So
9.
it is 9, yes. So why 9? Because when you complete the square, you take the thing in front of the first degree term, the 6, divide by 2, and square. So you take 6, divide by 2 is 3. 3 squared is 9. So what did I actually just do? I added 9, but really I subtracted 9, right? Because of the negative out here. So I added a minus 9. I can't just go around subtracting 9 whenever I want to. I also need to add 9. And now that is good. So I could rewrite at this point, this is the integral of d theta on top. On the bottom, I get the square root of, well, I get 36, and then I get minus theta plus 3 quantity squared. Does everybody buy that story? So that's why I completed the squares, so I could just write it as something squared, and that looks good. Now, this has the form of a sine inverse, correct? So what is the antiderivative of this thing? I've got like a d theta over a squared minus u squared. So what is the antiderivative? Can anybody tell me?
Sine inverse.
Yeah. Sine inverse?
Of u over a.
Yeah, it's of u over a. In this case, my u is theta plus 3. In this case, my a is what? 6. Yeah, so this is theta plus 3 over 6 plus c.
So the tan inverse is basically u squared plus the constant, or u squared plus.
Say that again.
So it would be 1 tan inverse, I guess well, so that's sine inverse, right? That's the form of sine inverse.
Yeah, sine inverse, like the traditional one,
Yeah.
looks like d theta over square root of 1 minus theta squared, right? That would be your sine inverse theta plus c, right? If this thing is something other than 1, if it's a squared, then how that changes is it becomes theta over a. In this case, we have theta plus 3 right here, but there's no, like the derivative of that thing is 1, so I can just use it as u, so to speak. If you wanted to, you could substitute for theta plus 3, but it really doesn't do anything.
And then if it was 36 plus theta plus 3,
Yeah,
that'd be cosine, right?
no,
Or would it?
no. It would be neither.
Oh, this is different.
It would be that, then you'd want to do a trigonometric substitution. Yeah, so it has to be a squared minus u squared, and then it's a sine inverse. If it's a squared plus u squared, then I would do a trig substitution using tangent. But I still have the square root, so it's not just tan inverse because of the square root. To be tangent, it would have to be a squared plus u squared without a square root, and then it would be a tan inverse.
And then the tan inverse is 1 over a tan inverse.
Yeah, for tan inverse, it's 1 over a tan inverse u over a. Yeah. Other questions? Somebody asked a question on here. Let me see. Let's see. Somebody's saying they can't see the board very well. That's a bummer. Let's see. Problem 6. Somebody asked for problem 60 on 8.6. Okay, sure. Oh, that's a fun one. Okay. Let me try to get a black pen. best, okay. So this is number 60 in 8.6. And it says integral from 0 to pi over 2 of e to the negative 3x cosine of x dx. Okay, and like I've said, maybe the hardest part of these problems is just diagnosing. And so what do you think?
My part is just gonna loop back on itself.
Yeah, this is similar to one I've done in the lecture, right, on the online stuff. There are two things here. Both of them, I know both the derivative of and the antiderivative of, which is great. I just have to choose which one to use as my u, which one to use as my dv. There's no right or wrong answer. So I think I'll just take the derivative of the e part and take the antiderivative of the cosine part. So I want u to be e to the negative 3x and dv to be cosine x dx. Then du is equal to negative 3e to the negative 3x dx, and v is going to be sine of x. Okay, so now I could make substitute in using my integration by parts, and I get u times v, which is e to the negative 3x times sine x minus the integral of v times du, which is negative 3e to the negative 3x. So I could pull the negative 3 outside the integral and make this a positive 3. I like that. Then I get e to the minus 3x sine x dx. And now I'm ready to do the same thing again. And it's very important that I keep whatever was my u before, I need to have that be my u again. I don't know if any of you have ever tried it the other way, but it's a bad day. And you basically unravel what you just did and you're left with what you started with. Yes?
I have to evaluate what it took out.
Oh, yeah, good point. So this is definite, isn't it? Yes. So this I should have put in and evaluated from 0 to pi over 2. Yeah, that's good. 0, pi over 2. Okay. Very good. So now we need to set up a u, e to the minus 3x, dv is sine x dx. We've got du is equal to negative 3 e to the minus 3x dx. V is, let's see, what would it be? Cosine goes to, okay, so negative cosine of x. Now we can rewrite. Okay, let's just leave everything alone for now and not start evaluating yet. So I have e to the negative 3x times sine x evaluated from 0 to pi over 2 plus 3 times u times v, which is negative e to the negative 3x times cosine of x. That one also evaluated from 0 to pi over 2. What? Minus the integral from 0 to pi over 2 of v du. I still have a negative 3 times a negative, so that's a positive 3. So I can bring out a positive 3 And then I get e to the negative 3x, e to the negative 3x times cosine x dx. All right, let's rewrite that again because that's kind of a mess. What I have here is I have this piece, which is e to the negative 3x sine x, evaluated from 0 to pi over 2. Then I have 3 of these, correct? So I get minus 3 e to the negative 3x cosine x, evaluated from 0 to pi over 2. And then I get minus 9 of these. So minus 9 integrals from 0 to pi over 2 of e to the minus 3x cosine x dx. Okay, but that's what I started with, right? Right here. So what I could do is I could add 9 of them to both sides of the equation. So I get 10 over here and 0 over there. So what I get is adding 9 of these over to this side of the equation, I would get 10 times the integral from 0 to pi over 2 of e to the minus 3x cosine x dx is equal to, and now let's go ahead and evaluate this. So if I plug in a pi over 2, what's sine of pi over 2? Yeah, that's 1. And if I plug in pi over 2 up here, I get e to the negative 3 pi over 2. So e to the negative 3 pi over 2 is when I plug in pi over 2. Then I subtract plugging in 0, but sine of 0 is 0. So I get minus 0. Okay. Now let's plug in here, and I get, let's see. If I plug in pi over 2, cosine of pi over 2 is 0, so I get plus 0 minus, plug in 0, cosine of 0 is 1, e to the 0 is 1, and so I just get minus 3. So I get minus 3. And that's it. Correct? All the rest, that integral was added to the other side. Now I just need to divide both sides by 10. And I get the integral from 0 to pi over 2 of e to the negative 3x cosine x dx is equal to, well, let's see what we have over here. We have e to the negative 3 pi over 2 plus 3. And we divided both sides by 10, so this is over 10. And that's our answer. Yes, sir.
So were you just trying to get the same thing as the original equation?
Yes, that's right. So I have some experience with this, and you do too, by watching. At least you've had to do at least one of these problems. But what you see is that like this is going to kind of loop. And when you see that like something's going to loop around, you want to get back to what you started with. And as soon as you do, you're sort of done. There's a little bit more work to do. But as soon as I see, okay, this is what I started with, then I just need to take all of those that I have, add them to the other side of the equation, and then solve for the integral. So that's the typical strategy on those. Does that make sense?
Yeah, how would you get 10 when you do that?
Why 10? Yeah, okay, so so I have a very long equation, but start at this side. I have left side equals right side, right? Or left side equals this, correct?
Yep.
So this integral equals that stuff. So now I say over here I have one of those integrals. Over there I have -9 of them. So what if I added 9 integrals to both sides? On this side, it would go away, correct?
Yes.
On this side, I'd get 1 of these integrals plus 9 of these integrals would give me 10 of these integrals. Does that make sense? So that's where the 10 came from, is I took the 9 that were on the left and added them to the 1 that was on the right. I do know my direction. I took the 9 that were on the right and added them to the 1 that's on the left. Make sense?
Yes, will we see a problem similar to this one?
It is possible. I won't promise but it's definitely a type that you've seen.
Okay.
Yeah. What else can I do for you? Okay, well, there's plenty of exercises online to watch if you want to watch some more. If you need to go somewhere to practice, go to Math Lab. I highly recommend it. I highly recommend, find a friend, work on some of these together. But if nothing else, work problems. Like just do a bunch of these problems to get ready. That's the best thing you can be doing, is just practicing, okay? All right, so I guess if you're in Group A or Group C, I'll see you Wednesday. If you're in Group B, I will see you Friday. Have a good day.